In the field of computer graphics, a shader is a computer program that is used to do shading, the production of appropriate levels of color within an image, or, in the modern era, also to produce special effects or do video post-processing. A definition in layman's terms might be given as a program that teaches a computer how to draw something in a specific and unique way. Shaders calculate rendering effects on graphics hardware with a high degree of flexibility. Most shaders are coded for a graphics processing unit, though this is not a strict requirement. Shading languages are usually used to program the programmable GPU rendering pipeline, which has mostly superseded the fixed function pipeline that allowed only common geometry transformation and pixel shading functions. With shaders, customized effects can be used. The position, hue, saturation, brightness, and contrast of all pixels, vertices, or textures used to construct a final image can be altered on the fly, using algorithms defined in the shader, and can be modified by external variables or textures introduced by the program calling the shader. Shaders are used widely in cinema post-processing, computer-generated imagery, and video games to produce a seemingly infinite range of effects. Beyond just simple lighting models, more complex uses include altering the hue, saturation, brightness and/or contrast of an image, producing blur, light bloom, volumetric lighting, normal mapping for depth effects, bokeh, cell shading, posterization, bump mapping, distortion, chroma keying, edge detection and motion detection, psychedelic effects, and a wide range of others. History. The modern use of shader was introduced to the public by Pixar with their RenderMan interface specification, version 3.0 originally published in May, 1988. As graphics processing units evolved, major graphics software libraries such as OpenGL and Direct3D began to support shaders. The first shader-capable GPUs only supported pixel shading, but vertex shaders were quickly introduced once developers realized the power of shaders. Geometry shaders were recently introduced with Direct3D 10 and OpenGL 3.2. Design. Shaders are simple programs that describe the traits of either a vertex or a pixel. Vertex shaders describe the traits of a vertex, while pixel shaders describe the traits of a pixel. A vertex shader is called for each vertex in a primitive. Thus one vertex in, one vertex out. Each vertex is then rendered as a series of pixels onto a surface that will eventually be sent to the screen. Shaders replace a section of video hardware typically called the fixed function pipeline, so called because it performs lighting and texture mapping in a hard-coded manner. Shaders provide a programmable alternative to this hard-coded approach. The basic graphics pipeline is as follows. The CPU sends instructions and geometry data to the graphics processing unit, located on the graphics card. Within the vertex shader, the geometry is transformed. If a geometry shader is in the graphic processing unit and active, some changes of the geometries in the scene are performed. If a tessellation shader is in the graphic processing unit and active, the geometries in the scene can be subdivided. The calculated geometry is triangulated. Triangles are broken down into fragment quads. Fragment quads are modified according to the fragment shader. The depth test is performed. Fragments that pass will get written to the screen and might get blended into the frame buffer. The graphic pipeline uses these steps in order to transform three-dimensional data into useful two-dimensional data for displaying. In general, this is a large pixel matrix or frame buffer. Types. There are three types of shaders in common use, with one more recently added. While older graphics cards utilize separate processing units for each shader type, newer cards feature unified shaders which are capable of executing any type of shader. This allows graphics cards to make more efficient use of processing power. Vertex shaders. Vertex shaders are run once for each vertex given to the graphics processor. The purpose is to transform each vertex's 3D position in virtual space to the 2D coordinate at which it appears on the screen. Vertex shaders can manipulate properties such as position, color and texture coordinate, but cannot create new vertices. The output of the vertex shader goes to the next stage in the pipeline, which is either a geometry shader if present, or the rasterizer. Vertex shaders can enable powerful control over the details of position, movement, lighting, and color in any scene involving 3D models. Pixel shaders, also known as fragment shaders, compute color and other attributes of each fragment. The simplest kinds of pixel shaders output one screen pixel as a color value. More complex shaders with multiple outputs are also possible. Pixel shaders range from always outputting the same color, to applying a lighting value, to doing bump mapping, shadows, specular highlights, translucency and other phenomena. They can alter the depth of the fragment, or output more than one color if multiple render targets are active. In 3D graphics, a pixel shader alone cannot produce very complex effects, because it operates only on a single fragment, without knowledge of a scene's geometry. However, pixel shaders do have knowledge of the screen coordinate being drawn, and can sample the screen and nearby pixels if the contents of the entire screen are passed as a texture to the shader. This technique can enable a wide variety of two-dimensional post-processing effects, such as blur, or edge detection enhancement for cartoon cell shaders. Pixel shaders may also be applied in intermediate stages to any two-dimensional images or sprites or textures or in the pipeline, whereas vertex shaders always require a 3D model. For instance, a pixel shader is the only kind of shader that can act as a post-processor or filter for a video stream after it has been rasterized. Geometry shaders are a relatively new type of shader, introduced in Direct3D 10 and OpenGL 3.2. Formerly available in OpenGL 2.0 with the use of extensions. This type of shader can generate new graphics primitives, such as points, lines, and triangles, from those primitives that were sent to the beginning of the graphics pipeline. Geometry shader programs are executed after vertex shaders. They take as input a whole primitive, possibly with adjacency information. For example, when operating on triangles, the three vertices are the geometry shader's input. The shader can then emit 0 or more primitives, which are rasterized and their fragments ultimately passed to a pixel shader. Typical uses of a geometry shader include point sprite generation, geometry tessellation, shadow volume extrusion, and single-pass rendering to a cube map. A typical real-world example of the benefits of geometry shaders would be automatic mesh complexity modification. A series of line strips representing control points for a curve are passed to the geometry shader, and depending on the complexity required, the shader can automatically generate extra lines, each of which provides a better approximation of a curve. Tessellation shaders. As of OpenGL 4.0 and Direct3D 11, a new shader class called a tessellation shader has been added. It adds two new shader stages to the traditional model. Tessellation control shaders and tessellation evaluation shaders, which together allow for simpler meshes to be subdivided into finer meshes at runtime according to a mathematical function. The function can be related to a variety of variables, most notably the distance from the viewing camera to allow active level of detail scaling. This allows objects close to the camera to have fine detail, while further away ones can have more coarse meshes, yet seem comparable in quality. It also can drastically reduce mesh bandwidth by allowing meshes to be refined once inside the shader units instead of downsampling very complex ones from memory. Some algorithms can upsample any arbitrary mesh, while others allow for hinting in meshes to dictate the most characteristic vertices and edges. Parallel processing. Shaders are written to apply transformations to a large set of elements at a time, for example, to each pixel in an area of the screen, or for every vertex of a model. This is well suited to parallel processing, and most modern GPUs have multiple shader pipelines to facilitate this, vastly improving computation throughput. Programming. The language in which shaders are programmed depends on the target environment. The official OpenGL and OpenGL ES shading language is OpenGL Shading Language, also known as GLSL, and the official Direct3D shading language is High Level Shader Language, also known as HLSL. However, CG is a third-party shading language developed by NVIDIA that outputs both OpenGL and Direct 3D shaders. Apple released its own shading language called Metal Shading Language as part of the Metal framework. See also, GLSL, GPGPU, HLSL, List of common shading algorithms, shading language, references. Further reading, Upstill, Steve. The Render Man Companion, A Programmer's Guide to Realistic Computer Graphics. Addison Wesley. ISBN A0-201-50868-0. Ebert, David S. Musgrave, F. Kenton. Peachy, Darwin. Perlin, Ken. Worley, Stephen. Texturing and Modeling, A Procedural Approach. AP Professional. ISBN A0-12-228730-4. Fernando, Randima. Kilgard, Mark. The CG Tutorial, The Definitive Guide to Programmable Real-Time Graphics. Addison Wesley Professional. ISBN A0-321-19496-9. Rost, Randy J. OpenGL Shading Language. Addison Wesley Professional. ISBN A0-321-19789-5. External links, OpenGL Geometry Shader Extension, Riemer's DirectX and HLSL tutorial using DirectX with lots of sample code, pipeline stages,